I am about to show you how AI solves impossible problems, but first, I'm going to need you to imagine you're a mountain climber, lost in a thick fog. Your challenge is to reach the highest peak, the absolute summit. But there's a massive catch. You can only see a few feet in front of you. So your strategy sounds easy, right? Always take a step in the direction that goes UP. Every single move has to lead to a higher elevation. It's this greedy, relentless pursuit of up. But what happens when you reach the top of a small hill, a minor peak, and you can't see the giant true mountain summit towering right next to you? From your tiny perspective, every direction is down. You're stuck. You think you've won, but you're not even close. This exact nightmare scenario is one of the biggest challenges in artificial intelligence, and it's perfectly explained by a simple but legendary algorithm called hill climbing. The problem: a world of infinite choices. Before we dive into the algorithm, you need to understand the insane scale we're dealing with. In AI, we are constantly facing problems of optimization, which is just a fancy way of saying we need to find the one best possible solution out of a mind-blowing number of options. Think about a delivery company trying to find the fastest route for just one truck to visit 100 different cities. The number of possible routes isn't just in the millions. It's a number so large it has more digits than there are atoms in the known universe. This is a famous challenge called the traveling salesman problem. Finding that single best route is an optimization problem. Or what about designing a new life-saving drug? Scientists have to find the one specific molecular structure that will fight a disease most effectively. Every possible way the atoms can be arranged is a different solution. That collection of every single possibility is the search space. That search space is the entire mountain range our AI has to explore, and the best drug is the highest peak, the global maximum. It's the same for training a machine learning model. Engineers have to tweak dozens of settings called hyperparameters. Every combination creates a model with a different accuracy. The goal is to find the one combination that makes the AI as smart as possible. We are literally searching for the highest peak of accuracy in a massive landscape. The real challenge here is the sheer scale. We can't just try every single option. If we tried to calculate every possible route for that delivery truck, the sun would literally burn out before we even made a dent. These are called NP-hard problems, which means as they get bigger, the time it takes to solve them perfectly just explodes. So we have a huge problem. We need amazing solutions, but we don't have infinite time. We need a cheat code. We need a strategy that can find a good enough solution ridiculously fast, even if it's not the 100% perfect one. We need a heuristic, and that's exactly where hill climbing comes in. It's one of the simplest, most intuitive cheat codes ever created, giving our AI one simple command: just go up. The solution: the simple logic of hill climbing. So, how does this insane algorithm actually work? Let's forget the foggy mountain for a second and get technical. The core idea of hill climbing is greedy local search. Let's break that down. Local search means the algorithm is not looking at the whole mountain range. It only cares about what's immediately around it, like our climber who can only see 10 feet ahead. Greedy means it always makes the choice that looks best right now, with zero thought for the future. It doesn't think, well, if I go down a little here, I might find a much bigger mountain over there. Nope. Its entire philosophy is, the next step has to be an improvement, or I'm not moving. Here's how it works, step by step. Step 1. Define the landscape. First, we have to build the entire world for the AI. This means defining all possible solutions, the state space, and how we measure if a solution is any good, the objective function. For our climber, the objective function is altitude. For the traveling salesman, it's the total length of the route. And in that case, we'd actually be hill descending, trying to find the absolute lowest cost. The logic is exactly the same. Step 2. Pick a starting point. The algorithm starts by picking a totally random solution. Think of it like we're dropping our climber from a helicopter onto a random spot on the mountainside. Step 3. Look at the neighbors. From its current spot, the algorithm checks all neighboring states. A neighbor is just a solution you can get to by making one tiny change. For the traveling salesman, a neighbor would be a new route created by just swapping two cities. Step 4. The greedy choice. Now the algorithm measures the height of all these neighbors and compares them to where it is now. And here's the greedy part. It picks the neighbor with the highest value, the single biggest step up. This is where you see a couple of different versions. Simple hill climbing. This version is super impatient. It checks neighbors one by one and immediately jumps to the first one it finds that's better. Steepest ascent hill climbing. This version is a perfectionist. It checks all the neighbors and then chooses the one that offers the absolute steepest climb. This is the most common version, and it's what we mean when we say hill climbing. Go big or go home. Step 5. Repeat or terminate. Once it moves to that new, better spot, the entire process repeats. Over and over and over, it keeps climbing higher. So when does it stop? It stops when it reaches a point where none of its neighbors are better. Every possible move is flat or downhill. The algorithm has reached a peak, and as far as it knows, it must be on top of the world. For some problems, this is unbelievably effective. It uses almost no memory and can find a solution in seconds. But this simplicity is both its greatest strength and its most profound, fatal flaw. This blind, optimistic climber is walking straight into a landscape full of traps. The fatal flaw. The traps that fool a greedy climber. We've now arrived at the algorithm's fatal flaw. It stops when it can't find an uphill step, thinking it has found the ultimate solution. But what if it's wrong? The search landscape is filled with traps that cause it to stop way too early at a solution that is not the best one. Trap 1. The local maximum, the false summit. This is the most famous trap. A local maximum is a peak that's higher than everything right around it, but it isn't the highest peak in the entire world. The true highest peak is the global maximum. Imagine our climber. They've been climbing and climbing, and finally, they reach a spot where every direction leads down. They plant their flag and declare victory, convinced they've just conquered Mount Everest. But the fog is hiding the fact that they're on a tiny foothill. The real mountain is a quarter-mile away and thousands of feet higher. They're at a peak, but it's a local one. To get to the real summit, they would have had to go down first, cross a valley, and start climbing again. The hill climbing algorithm is completely incapable of making that move. It has zero long-term strategy and will never choose a move that makes things worse. It gets stuck on the false summit, completely blind to the much better solution just over the horizon. This is the single biggest weakness of the hill climbing approach. Trap 2. The plateau, the perilous flatland. The next trap is even weirder. A plateau is a totally flat area where all the neighboring spots have the exact same value. Our climber suddenly finds the ground has leveled out. They take a step forward, left, right, no change in altitude. Every direction is sideways. Since the algorithm is only looking for a better state, and none of these are better, it has no reason to move. In most cases, this makes the algorithm just give up and terminate. It gets stuck on this boring, flat expanse, never knowing if the ground started rising again on the other side. Trap 3, the ridge, the narrow ledge. This third trap is crazy. A ridge is a long, narrow crest where the only way up is to walk a very specific line, but stepping off to the side means a massive drop. Our climber is on one of these ridges, and the summit is straight ahead. But let's say the algorithm is only allowed to check its neighbors north, south, east, and west, while the ridge runs diagonally to the northeast. A step north takes them off the ridge, and the altitude plummets. Same for east, south, and west. The only way up is a diagonal step, but that's not a neighbor the algorithm is allowed to check. Because every valid move leads downhill, the algorithm gets stuck again, unable to see that the true summit was right there. These three traps, local maxima, plateaus, and ridges, are the Achilles heel of simple hill climbing. They prove that while its greedy strategy is fast, it's also incredibly naive. This forced computer scientists to get creative and invent insane ways to help their blind climber escape. The fixes. Teaching the climber new tricks. Knowing that basic hill climbing gets stuck, researchers saw this and said, "No way, we can fix this." They invented some insane upgrades to give the climber a better chance of finding the true summit. These are all about answering one question. What do you do when you get stuck? The escape route, random restart, hill climbing. The most common fix for the false summit problem is brilliantly simple. Random restart hill climbing. What do you do when your climber is stuck on a tiny hill? You literally call in a helicopter, pick them up, and drop them on a completely new random spot to start the entire climb over again. The random restart strategy runs the whole steepest ascent algorithm hundreds or even thousands of times, each time from a different random starting point. The first run might get stuck at a peak of 1,200 feet. It saves that result. The next run starts somewhere else and gets stuck at 3,500 feet. It keeps that new, better result. This process repeats over and over. At the end, it just returns the best peak it found across all of its climbs. By starting from so many different places, it dramatically increases the odds that at least one of those climbs will start on the slopes of the real Mount Everest. A little bit of randomness, stochastic hill climbing. Another version, stochastic hill climbing, adds a little bit of chaos to the greedy decision. Instead of always picking the absolute best uphill neighbor, it picks one at random from the set of all possible uphill moves. Why would you do this? On certain complex ridges, it might choose a less steep, but ultimately better path. While it doesn't solve the false summit problem by itself, it forces the climber to explore. Two runs from the same starting point might follow completely different paths and end up on different peaks, which the original version could never do. A more daring move, accepting bad steps with simulated annealing. But this is the ultimate upgrade. It's a more powerful algorithm called simulated annealing. It directly attacks the core flaw of hill climbing, its refusal to ever take a downhill step. Inspired by the process of making metal stronger by heating it up and cooling it slowly, this algorithm does the same thing. It always accepts a better move, But here's the game-changing difference. If a neighbor is worse, a downhill move, it might still go there anyway. The chance of it making a bad move depends on a temperature variable that starts super high and gradually cools down. When the temperature is high, the algorithm is in full-on chaos mode, happily jumping all over the landscape and easily escaping those tiny hills. But as the temperature cools, it becomes more and more conservative, eventually behaving almost exactly like standard hill climbing. This ability to take downhill steps is what allows simulated annealing to cross entire valleys and find new, taller mountains. It's a hill climbing algorithm that has learned that sometimes you have to take one step back to take 1,000 steps forward. Real-world applications. Where is hill climbing used? You might be thinking, this sounds broken, but this algorithm, especially with the helicopter restart trick, is used for crazy real-world stuff. It's perfect for when you need a good enough solution, and you need it now. Robotics and pathfinding. In video games, AI characters use this to find the best place to hide or get the perfect shot. They are literally hill climbing to get a tactical advantage over you. Scheduling and optimization. Huge companies like airlines use it to assign crews and planes to flights to slash costs, or factories use it to make their production schedules insanely efficient. Machine learning. While newer methods are common, hill climbing is still a quick and dirty way to tune the settings of a machine learning model, turning a dumb model into a super smart one by finding the best combination. Classic AI puzzles. It's famous for tackling legendary challenges like the Eight Queens problem and the hard-traveling salesman problem. It might not find the 100% perfect route for the salesman, but it will often find a 99% perfect route in a fraction of the time. Conclusion. The first step. Up. A much bigger mountain. So what did we just learn about our climber in the fog? We've learned that hill climbing is a ridiculously simple, super fast algorithm that has one goal. Just go up. It's fast, efficient, and doesn't need a supercomputer to run. But we've also seen its profound, fatal flaw. Its limited view makes it vulnerable to getting trapped on false summits, flatlands, or narrow ridges. It finds peaks, but it can't promise it's found the highest peak. Understanding this failure, though, is a rite of passage in AI. It perfectly shows the battle between speed and perfection. The need to escape these traps is what led to even smarter algorithms like random restart hill climbing and simulated annealing. And even today's most advanced AI are all just finding cleverer ways to solve the same problem. How to find the highest peak in a vast and foggy mountain range. Hill climbing is a foundational concept. It may not always get you to the summit, but it teaches you exactly why the climb is so incredibly challenging in the first place. Tate. If this explanation helped you understand the insane challenges of AI, destroy that like button. Let me know in the comments what other AI concept you want me to break down next. And if you want to keep climbing these mountains of knowledge with us, make sure to subscribe and hit that bell so you don't miss the next expedition. Thanks for watching.